Hello everyone, and welcome to this video on the pathfinding and graph traversal algorithm known as A*. Now, the A* algorithm has a variety of applications from solving an 8 puzzle all the way up to deciding the movements of a mobile robot. So we're going to be looking at how that works and some of the features it contains. So to start off with, if we have a node under consideration, for example n, and it has neighbours x, y and z, we're going to want to know which neighbour to expand from n. The way the A* algorithm does this is by using the cost function denoted here by f of n, and this is basically equal to the move function plus the heuristic function. Now the move function is the current cost of our path up to the point of n. So it's basically the shortest path that we currently have, and if we were to add on x, y or z, then we'd add on how much this would actually cost us. The heuristic is a prediction made beforehand about the potential cost from the neighbours x, y and z to the actual goal state. So combining a prediction with the actual cost that it would take to get from n to one of its neighbours, we can then define the cost function and find out which neighbour is actually best to expand to find the shortest path. So looking at some of the features of A* algorithm, we know that it's optimal, which basically means it's always going to find the shortest path. If we give it a graph, it's always going to find that optimal solution in the graph. And this is because if we have a path to the goal state, this doesn't necessarily mean that it's going to be the shortest path. A* knows this and it keeps it in an open list, checking for other potentially shorter paths. The way it does this is by using an admissible heuristic, which means that the prediction from a node to the goal is always going to be an underestimation of the true cost. This means we can stop exploring a new path if the total cost is greater than the path that we have discovered to the goal, which makes sense. It also means that if we can discard a path as soon as the estimated cost is greater than the total cost of a known path. And this is because the true cost will always be more than the estimation anyways. So A* is also complete, which means that it's always going to find a solution if one is available. And this makes sense because if you think about it, A* is very similar to BFS. It's just a guided version of that. We're basically checking a node and we're checking all of its neighbours that could be a shortest path, which means we're going to have to check every single neighbour. So it's similar to BFS in that way and means that it's complete and it will always find a solution to the goal if one is available. These are two positive features of A*. However, one negative of this is that the space and time complexity suffer. In A*, there are big O notation b to the power of d, whereby b is the branching factor, the average number of children from each node, and d is the depth of the solution, the number of nodes from the start node to the end node. And this is obviously a worst case scenario, whereby if we have a constant heuristic and we have to check every single neighbour of every single node, we're going to get our time complexity and space complexity of b to the power of d. In most cases, if we have a good heuristic, it's going to be slightly better, but this is still one of the weaker points of A* algorithm. So now we need to actually look at an example of how A* algorithm is going to work. So I've got this graph here. The blue numbers are going to be our heuristic value for that prediction from the node to the end node, and then we've got the white numbers, which are going to be the actual cost of the path. So the way that I'm going to show how A* algorithm is working is using a table. The columns here are just the node under consideration, the move function, the heuristic function, the cost function, and then the previous node from that path. So A is going to be our start node, and then H is going to be our goal node. So we're starting with A here, and we're going to move A into the open list, which is basically just saying we haven't checked all of the neighbors of this node yet. So A is our node under consideration. G is the move function, which is basically saying we haven't moved anywhere yet. So the move function for our start node is always going to be 0. We've then got our heuristic value, which is going to be 15, which is a prediction from A to H. And then we've got our cost function, which is going to be the move function plus the heuristic function. We're then going to expand A and look at the neighbors of A. So we've got B, we're going to add that to the open list, and we've got C, which we're going to add to the open list in a minute. We're now going to fill in the table for B, and we're going to fill in the table for C. The move function for these nodes is going to be how much it actually costs for moving from A to B and A to C. We're then going to add the move function to our heuristic function to give the final cost function values of these two neighbors. And then the previous node from B and C is obviously A. And the reason why we use the previous node is so that we can find the shortest path and we can unravel it on the way back. So now we have looked at all of the neighbors of A. So we can move A from the open list to the closed list, which is basically just saying we've now looked at all of the neighbors of A and that is fully complete. Now, the reason why we expand B in this case is because B has the lowest cost function. If we look at all of the cost functions here, B is 11, which is the lowest cost function compared to the others. So that's the one we're going to expand. B only has one neighbor, which is G. So we're going to check G and we're going to add this to the open list. We're going to then fill out all of the features of G. Now, the cost function is going to be the move function plus the heuristic function. The move function is interesting here as it's going to be the cost of two of the paths added together. So we constantly add the paths together to get our move function, whereas the heuristic function is just going to be from that node under consideration. We're not going to add the heuristics together. So G is going to be added to the open list, and B is then going to be moved down to the closed list because we've looked at all of its neighbors. It only has one neighbor, which is G. We're then going to be looking at C, and the reason why we're looking at C is because we've now checked out B, so we don't need to look at its cost function. We've checked out A, so we don't need to look at its cost function either. We only have two possibilities for the cost function, C at 14 or G at 18. So obviously we're going to take the lower cost function because we're looking for the shortest path. So that's why we're going to expand C in this case. C has three neighbors, E, D, and F. So we're going to fill out the features for E. We're going to fill out the features for D. And we're going to fill out the features for F. And they're all going to be added to the open list. This means we've now completed C, and C can move down to that closed list. Now looking at the cost functions, our lowest cost function is going to be E at 15. So we're going to expand E and look at E's neighbors. E only has one neighbor like B, which is G. In this case, this is interesting because we've actually already found a shorter path from B to G. E to G is actually a longer path, and we don't want this. So we're going to cancel out the path from E to G, and this is shown by the purple arrow. And we're not going to update the features of G because the shortest path is from B, which is already added on from G here. and we're not going to change the previous one in this case. We then move E from the open list to the closed list, and this is because we've now checked all of E's neighbors. We're then going to change the node D, and the reason why we're going to do that is because we're now looking at F. F had the lowest cost function at 16, so we're going to expand F's neighbors. F only has one neighbor, which is D, so we're going to change D, and the reason why we're changing the features of G is because we've actually found a shorter path to the node under consideration, which is D. C to D is actually a longer path. So we're going to be changing the features here. We're going to be removing that previous node C, and we're going to be changing it to F as we found a shorter path. So we're going to be updating the features. We can then say that this path is no longer the shortest, so I'm going to indicate that by purple. We've then looked at all of the neighbors of F, which is only one, which is D. So we're then going to move F down to the closed list, basically saying that it's complete. Now looking at the nodes left, we either have G, which has a cost function of 18, or D, which has a cost function of 17. We're going to be looking at the shortest cost function, the smallest one, which is going to be 17. So we're going to expand D. D only has one neighbor, which is H. This is the first time we've seen H, so we're going to add it to the open list and fill out the features. For H, it has a heuristic of 0. Because it is the goal node, there's no need to predict anything because we've already hit the goal node. So now we've completed D as we've looked at all of its neighbors, so we can move D from the open list down to the closed list. We have G left in the open list that we still need to look at. So this is where the admissible heuristic has come in, because we have found a path from A to H. We've found that path from the start node to the goal node. However, there could potentially still be a shorter path as we haven't checked G. G is still in the open list, which means it could still potentially be a shorter path. As we've used that admissible heuristic, which is an underestimation, we know that G could still potentially have a true value that is shorter than a path that we've already discovered to the goal state. So we're going to keep looking. In this case, G actually has a longer path, and we can then move G from the open list to the closed list as we've looked at all of its neighbors, just being H in this case. That completes all of the nodes and all of the possible paths to H, as we've only got the goal node left in the open list. To finalize this video, I want to show you a visualization created using Python that I have altered to show squares within a grid, each of varying difficulty. So I've created it so the darker squares are more difficult to cross and the lighter squares are easier to cross. So when we have a start square and an end square, the A-star algorithm will find the shortest path between these two. And this visualization shows this. And that concludes this video on the A-star algorithm. Thank you for watching.